Hello everyone, welcome to the second lecture in the lecture series on gas turbines. My name is Vinod. So in the previous lecture, we focused basically on the concept of gas turbines, its classification, that is the open cycle, closed cycle. I've introduced the Brayton cycle, and I've also, I believe I've completed the derivation on the thermal efficiency or air standard efficiency of the Brayton cycle. I've discussed certain performance parameters, and this lecture, that is in our second lecture, I'll be discussing more on the other performance parameters. The first one being the air-fuel ratio. Air-fuel ratio, as you all know, is defined as the ratio of mass flow rate of air to mass flow rate of fuel. The maintenance of proper air-fuel ratio is necessary for efficient combustion to take place inside the combustion chamber. Now, the second performance parameter is the turbine power, that is the turbine power that we get from the cycle, that is equal to, represented as WT, that is equal to m dot A into Cp into T3 minus T4. Here, instead of Cp, right, instead of Cp, we will be writing it as, for turbine, it is Cp is equal to Cpg, because exhaust gases are being produced in the combustion chamber in the real case, right, in the real case. So, unless otherwise mentioned, what we will do is, if the value Cpg is given, Cpg means specific heat of constant pressure for exhaust gas. If the value is given specifically, then we will write it as m dot A into Cpg into T3 minus T4. And the third one is compressor power. The power required to drive the compressor, that is equal to Wc, that is equal to m dot A into, again instead of Cp, I have to write it as Cpa, because in the compressor, fresh air is being supplied. So Cp, that is equal to Cpa, which means specific heat for air. So m dot A into Cp into T2 minus T1, both of the units are involved since it is power. Now, the net power in the cycle is equal to Wt minus Wc, that is work done by the turbine minus work done by the compressor, and heat supplied in the cycle, that is equal to m dot F into Cv, right? That m dot F represents mass flow rate of fuel into Cv represents the calorific value of the fuel. Usually this expression is used because the terms mass flow rate and the calorific value will be either given, or the air fuel ratio will be given, from which we can find the mass flow rate of fuel we used, multiplied by the calorific value, will get the heat supplied. Otherwise, we have another equation, that is m dot A into Cp into T3 minus T2. Okay. So these are the performance parameters. Now we go on to another performance parameter, which is the turbine efficiency. Because while analyzing the closed cycle, what we assumed is that the process was isentropic, that is the expansion process that is taking place inside the turbine was assumed to be isentropic, but in the real case, it is not isentropic, it deviates from the isentropic behavior, right? As you can see, 3 to 4 is the isentropic expansion process taking place inside the turbine, but the actual expansion process is 3 to 4 dash. So the endpoint 4 dash has a higher entropy compared to 4, right? That is, this 3 to 4 dash is the actual expansion process that is taking place inside the turbine. Okay. Now, we can easily find two works, right? Two work outputs. That is, first one, the actual work, because 3 to 4 dash represents the actual expansion process in the turbine. Therefore, W actual is equal to Cp into temperature at 3 minus temperature at 4 dash. That is Cp into T3 minus T4 dash, where T3 minus T4 dash represented here represents the actual temperature drop that is taking place inside the turbine. Now, 3 to 4 is the isentropic expansion that is taking place. So, similar to actual work, we can also find the isentropic work or ideal work that is produced in the turbine. So, the ideal work output from the turbine or isentropic work produced will be equal to Cp into the temperature difference. Temperature difference here will be T3 minus T4. Therefore, W ideal or W isentropic will be Cp into T3 minus T4, where T3 minus T4 is the isentropic temperature drop, T3 minus T4 dash is the actual temperature drop. So you can define the efficiency of a turbine as the ratio of actual turbine work output to isentropic work output. So the actual turbine output will be Cp into T3 minus T4 dash, isentropic work will be Cp into T3 minus T4. Cp values will get cancelled. So what you will get is turbine efficiency is equal to T3 minus T4 dash by T3 minus T4. Okay, that is the isentropic, the actual turbine, that is turbine efficiency. You can also define it as the actual temperature drop to isentropic, ratio of actual temperature drop to isentropic temperature drop. Now, we move on to the last one, which is the compressor efficiency, right? Compressor efficiency in a gas turbine. Similar to the turbine, the isentropic, the compression process inside the compressor was assumed to be isentropic. That isentropic process is represented by 1 to 2. But in an actual compressor, the compression process is not isentropic. That deviation in the isentropic behavior is shown by the curve 1 to 2 dash. So 1 to 2 represents the isentropic work input required for the compressor, and 1 to 2 dash represents the actual work input required for the compressor. Now, the isentropic work input required for the compressor is W isentropic or W ideal is equal to Cp into T2 minus T1, where T2 minus T1 represents the temperature rise, isentropic temperature rise in the compressor. Now we can also find the actual work input required for the compressor, that is W actual is equal to Cp into T2 dash minus T1, where T2 dash minus T1 shown here represents the actual temperature rise that is taking place inside the compressor. So similar to the turbine efficiency, I can also write compressor efficiency, but there is a difference. Compressor efficiency here will be equal to the isentropic compression work, ratio of isentropic compression work to actual compression work. That is, isentropic compression work will be Cp into T2 minus T1 divided by Cp into T2 dash minus T1, where the Cp value will get cancelled. So what is remaining is T2 minus T1 divided by T2 dash minus T1. That is, compressor efficiency can be defined as a ratio of isentropic temperature rise in the compressor to actual temperature rise in the compressor. So these are the main performance parameters that we are using. So hope you understood actually the concepts that have been discussed here. So next we will be moving on to the derivation for optimum pressure ratio. This is a very important derivation because it has been asked multiple times in the university examinations. Now the main step is we'll be first initially writing, because we need to find the optimum pressure ratio in order to obtain maximum W net, right? So work net I will be writing it here. W net is equal to, as you all know from the definition, it is the difference between the turbine work and the compressor work, Wt minus Wc. From the graph, because you have to draw the graph also, right? You have to draw the schematic for a closed cycle or the Brayton cycle, and you have to also draw the PV diagram and TS diagram for the Brayton cycle before you write the derivation. So kindly note it that you have to draw, again I'm repeating it once again because you have to draw, it's very important, that is, you have to draw the PV and TS diagram for a Brayton cycle as well as a schematic for a Brayton cycle. Okay. So again, we'll move back to the derivation. So W net is equal to, instead of work done by the turbine, I can write it as Cp into T3 minus T4 minus, instead of compressor work, I can write it as Cp into T2 minus T1. I am completely taking Cp here common. Then inside I'll have T3 minus T4, where I'll be taking T3 common. So within the bracket, what is remaining is 1 minus T4 by T3 minus, I'll be taking T1 here common. So within the brackets, T2 minus T1 minus 1. Okay, and I'll be writing it as equation 1. Now, similar to the derivation where we derived the thermal efficiency for a Brayton cycle, I'll be finding an expression for T3 in terms of T4 and T2 in terms of T1. Okay. So again, similar to the Brayton cycle derivation, 1 to 2, the process taking place inside the compressor is assumed to be isentropic. So I can write P2 by P1 equal to T2 by T1 all raised to gamma by gamma minus 1, where P2 by P1, as we already discussed, is a pressure ratio, that is equal to T2 by T1 the whole raised to gamma by gamma minus 1. So here I can write T2 is equal to T1 into pressure ratio raised to gamma minus 1 by gamma. From there I can write the ratio for T2 by T1. So I'll be getting an expression for T2 by T1. So T2 by T1 is equal to pressure ratio raised to Z, where Z is equal to gamma minus 1 by gamma. Right? I've written Z in order to simplify the equation so that the derivation will become a bit easier. So an initial ratio, I found the ratio for T2 by T1. So here they have T2 by T1. So I found out an expression. Next is I need to find an expression for T4 by T3. For that, I'll take the process 3 to 4. 3 to 4 is also, and I assumed for our ease of analysis, the expansion process in the turbine is represented by T4, which is also an isentropic process. So here I'll write T3 by P4 is equal to T3 by T4 the whole raised to gamma by gamma minus 1, where P3 by P4 is again the pressure ratio. Pressure ratio is equal to T3 by T4 the whole raised to gamma by gamma minus 1. From here I can write T3 is equal to T4 into pressure ratio raised to gamma minus 1 by gamma. Instead of gamma minus 1 by gamma, I can write it as Z. So I will get T3 is equal to T4 into Rp raised to Z. From where I can write T4 by T3 will be equal to 1 by Rp raised to Z. So instead of T2 by T1, I can write it as Rp raised to Z, and instead of T4 by T3, I can write it as 1 by Rp raised to Z or Rp raised to minus Z. So I'll be substituting both these equations, that is T2 by T1 and T3 by T4 in equation 1. Once I substitute in equation 1, what I'll get is Cp into T3 into within brackets 1 minus 1 by Rp raised to Z minus T1 into within brackets Rp raised to Z minus 1. And again, when I simplify, I can write 1 by Rp raised to Z as Rp raised to minus Z. That is what is written here. Okay. Now, okay, so I think I will mark this as equation 2, right? I'll take this as equation 2. This is the expression for W net in terms of Cp, T1, T3 and pressure ratio Rp. Okay. Now, if you take this equation, this is equation 2. In equation 2, T1 represents the ambient temperature, right? The ambient temperature we cannot control because air is taken from outside. So T1 is almost, can be assumed, right? There won't be much temperature variation in the case of atmospheric air. So T1 is actually a constant. T3 is also a constant because T3 we have to restrict the temperature in the combustion chamber to a safer temperature limit. So beyond that temperature we cannot move upward, or we cannot provide, or we cannot increase the temperature further beyond a particular value. So T3 is also actually a fixed parameter when you design a turbine. The Cp value is also fixed, right? So the only parameter that you can vary here is the pressure ratio. So in order to get maximum W net, you need to differentiate expression 2, that is this equation 2. This equation 2 you have to differentiate with respect to the pressure ratio and equate it to 0 in order to get maximum work, right? So dW net by dRp is equal to 0. So I'll substitute here. The derivation is quite simple, right? That you can do it for yourself. So derivations will be there, and I'll get an expression for T3 by T1, right? The derivation steps are being written here. You have to write the derivation in order to get a clear idea. Derivation steps are written here. Finally, after completing the derivation, what I'll get is the ratio for highest temperature to lowest temperature, that is T3 by T1, that is equal to Rp raised to Z minus 1 into Rp raised to Z plus 1. That is equal to what I'll get is Rp raised to 2Z. That is the optimum expression for optimum pressure ratio. In order to get maximum W net is T3 by T1 the whole raised to 1 by 2Z, or T3 by T1 the whole raised to gamma by 2 into gamma minus 1. This portion, or Rp, this equation is the optimum pressure ratio. This optimum pressure ratio, if maintained, will actually give you maximum W net. From there we can also calculate an expression for WR. The steps are being written here, right? That you can easily just write it down. Finally, what I'll get is work ratio will be 1 minus T1 by T3 into Rp raised to Z. So this derivation is actually very, very important. The expression for optimum pressure ratio is very important. It's being continuously asked in your university examinations. Okay. So again, we come to the end of this lecture. In the next lecture, I'll be discussing on the methods to increase the turbine work, the net to work, and even the thermal efficiency of a Brayton cycle. There are different methods: intercooling, regenerative heating, as well as reheating, that I'll discuss in our next lecture. This is the third video lecture. So thank you, and again I'm reminding you this expression, that is the derivation for pressure ratio, is very important, right? You have to learn it properly. Okay, so thank you.